Hey, welcome back to Math with Patrick. Today's August 16th, and we're solving problem number 228 from the Daily Epsilon calendar. And we should figure out why x should be 16 for today. So this number, that number should both match today's date. And like the last video, I don't have my drawing pen for my little drawing pad, so my handwriting is going to be a little bit poorer because I am using my mouse. And so I'm seeing that we have the square root of log base 16 of x plus 3, and then plus the square root of log base 2 of x plus 12 is equal to 6. So I'm thinking of a few things right now that we have two numbers essentially added together equals 6. And so I'm hoping that maybe these are going to be whole numbers. We could kind of guess and check. That could be a valid solution here. Also, maybe it would even be 0 plus 6. That could be a possibility here. And so we could try guessing and checking and trying things out and seeing if we get a solution that way. Also, the opposite of square roots is squaring. And so there might be a solution by doing something about squaring both sides to hopefully get rid of these square root signs. Log base 16 of x versus log base 2 of x. I'm also thinking about those. And this number, I believe, is always greater. For example, and I'm going to use 16 as my example here just for show. Log base 16 asks, how many 16s do we need to multiply to each other to get to the number 16? And so this one is quite obviously just 1, because you just need the 116. And if we asked log base 2 of 16, this is asking us how many 2's do we need in a multiplying way, like powers of 2, to get to the number 16. So we could do 2 times 2 is 4, times 2 is 8, times another 2 is 16. And since it took 4 2's to get to 16, log base 2 of 16 is 4. This 16 could have been a 32 or a 64, and the example would have been about the same. Although I guess maybe we would want powers of 16 right here to make the math a little bit easier. So maybe 256 would be another number that we could have used to kind of get an understanding of what's happening with these logarithmic expressions. Ultimately, what I wanted to show, though, is I can tell that this value right here is essentially always going to be less than this value right here. And then not only that, plus 3 is not doing as much as plus 12. So this guess and check method is actually not that bad, because I can tell that this number should be quite larger than that one right there. So we're in the territory of maybe doing 0 plus 6 equals 6. Maybe it's 1 plus 5 equals 6. Or maybe it's going to be 2 plus 4 equals 6. But it's definitely not going to be 3 plus 3 equals 6, because this is when they have equivalent values. So we could try backtracking from these ideas and seeing if we can produce an answer, just hoping that these are both integer values. This first one isn't going to work because there's I guess there is a way for this to be a 0. It is possible for log base 16 of some number to be -3, right? Because I'm imagining if this were a -3, then I'd have -3 plus 3 is 0. Square rooting 0 gets you a 0. And then to unravel logarithmic expressions back into exponential expressions, here's our base, 16. Here's our exponent, -3. And then here is our argument, x. So it is possible for us to plug in 16 to the power of -3, which is whatever this number is, into x. We could get a 0 here. Then we'd have to use this mystery value and plug it in here and see what happens. I guess we could do that. Log base 2 of 16 to the power of -3. There's a log rule where if you have an exponent in here, you can bring it out front as a multiplier or a coefficient. And then log base 2 of 16, we just saw, is 4, right? 2, 4, 8, 16. So overall, this number could be negative 12. So it looks like if we force this value to be negative 3, this value happens to be negative 12, and we get into this 0 plus 0 scenario, which definitely isn't 6. So guessing and checking there, we can't do 0 plus 6 because just the math doesn't work out. And I'm inclined to just try guess and check 2 more times, just because, well, it's only 2 more times. It won't take that long. If we assume that this value is 1, then we must be square rooting the number 1. So this right here must be the number negative 2. And so we can run through kind of the motions there again. We could ask what would happen if log base 16 of x is equal to negative 2. We can unravel the logarithmic equation as an exponential one. We can isolate our x, 1 over 16 squared. We can see what happens when we plug it into this log base 2 of, you know what, I will just do 16 to the power of negative 2 because that way I can use that log rule again. And then this is, once again, the number 4. And so overall, we get the number negative 8 right here. So if we decide this is the number negative 2, then this number is forced to be the number negative 8. Then we get the square root of 1 plus the square root of 4, and 1 plus 2 is not equal to 6 yet. So I'm guessing 2 plus 4 is actually the way to go here. And we should see what happens when we try 2 plus 4. So this right here should be the number 4 with our guess and check method. And so that would imply that log base 16 of x is equal to 1. We saw earlier that this number right here would need to be 16. And so we're kind of on the right track for figuring out that x indeed is 16. So if x is 16, this is the number 1. Square rooting 4, we get 2. If x is 16 right here, this right here is the number 4. Adding a 12 gives us 16. And then square rooting the 4 plus 12 gives us the number 4. So it turns out that a little bit of guess and check with some integers shows us that x needs to be 16 for today. I did find an algebraic way to solve this equation too, which doesn't rely on guess and check and might be a little bit better. And it relies on these two expressions being pretty similar to each other. And first I want to draw a similarity between the two log expressions here. Log base 16 of x and log base 2 of x. So just based on the underlying meaning of logarithms, whenever you have an expression like this, it's kind of asking how many 16s do you need to multiply altogether to get to some number x. So bringing in that 256 as an example, we can see that 256 is just 16 times 16. We can see that it takes 2 16s to get to this number, and therefore the answer is 2. And if we tried doing log base 2 of 256, we're just basically counting how many 2's we need to multiply altogether to get to this number. So interestingly, we can start with the 16 times 16 factoring. And as long as you know that 16 is just 2 times 2 times 2 times 2, you can see a similarity between the two of these. Essentially, every time that we count one of our 16s in this expression, we're counting 4 2's in the other one. So for every 16 I see here, in this case there are 2 of them, I need to multiply my resulting answer by 4 to get the correct amount of 2's over in this expression. So not too bad. And this basically shows me that whatever this number is, the 256 wasn't anything special. Whatever answer I get over here, I am allowed to just multiply that number by 4, and then I get this number over here. And what's nice is that this lets me either remove this log base 2 expression or this log base 16 expression. And I think it'll be nice to actually remove this one just to show the algebra. So let's write it all out. Square root of log base 16 of x plus 3 plus, and then I'm going to do that substitution here, replacing this bit with 4 times log base 16 of x plus 12 is equal to 6. My idea here is that both of these terms have a 4 in it, and so I could actually factor out this 4 of the 12 and make it a 3. And I'll just put parentheses here, so now like if I distributed that 4 again, I'd get back to where I started. And anytime that you have a product in square roots, you are able to split them. So like root like 15 is the same thing as root 5 times root 3. So you can kind of distribute the square root over multiplication. So ultimately that gives me root 4 times root log base 16 of x plus 3. And this root 4 is just the number 2. And then now I have 2 of this expression plus 1 of the exact same expression. So overall, I get 3 of that expression. And this was a simplification that I noticed actually after 20 minutes of filming a completely different strategy. I'm filming this episode out of order. So once we do these algebra steps here, I will show you my other idea. It takes quite long, so no pressure to watch all of that. But it is a different way to approach this problem entirely, and so I'm going to include it in the video because, why not? Anyhow, we're down to this part of the algebra here. And if we have the square root of some number and we're getting 2, the only way for us to get the number 2 is if all this stuff underneath the square root sign is 4. Or in other words, we could just square both sides of the equation and knock those out. We get log base 16 of x plus 3 equals 4. We have some number plus 3 is 4, so the only way for that to be true is if our number right here is the number 1. So log base 16 of x is 1. And then just like we were talking earlier about how like when this number is a 16, we only need the 116 to multiply up to that number. That's essentially what I'm seeing here, where, what mystery number is this? Well, it's got to be a 16. Another way to think about it, though, you can always rewrite logarithmic equations as exponential ones, where this is your base, this is your exponent, and this is your answer. And so 16 to the power of 1 is just 16, and that is the answer for x. So there we go. That's probably the best solution here, is noticing the similarity in structure between the two and solving for x. Though stick around if you want a long, convoluted way to solve this. Maybe more generally if we didn't happen to have that neat similarity. Anyways, I'll see you tomorrow, and stick around if you want solution number 3. I'm actually going to use Desmos to show my work. Again, limited by the fact that I don't have my pen right here. But I actually do this sometimes, even if I do have a pen or pencil and paper. Because as I'm doing these algebra steps, I can actually take a look at the graph to just double check that my algebra steps aren't messing up my answer. So right now, this vertical red line right here is showing that we have an answer of 16, as in this is the one and only x value pretty much anywhere on the graph that produces a line. And that's indicating to me that this is the same thing as just saying x equals 16. You can now see that this blue line kind of overlapped the red one. And that kind of shows me that they are the same thing. So to try to solve it algebraically, I wanted to try squaring both sides to kind of get rid of the square roots. And I think it might be nice to subtract this quantity to the right side first. I could have picked this one as well before I start squaring stuff, because once I square stuff this way, I feel like I'll get fewer square roots in the end. It's almost like I'm canceling this one with that one. So squaring the left-hand side, that will go away. And then squaring the right side, I will need to distribute everything. We will get the first times the first, which is 36. We will get 2 times the product of these things. So it's going to be a minus 12 and then that square root. And then finally, we will add on the square of the last term, which is just going to be that term without the square root sign. So if I copy and paste all this stuff over here, this is basically squaring both sides. And to confirm that my algebra is making sense, I can kind of hide the green line and show that it's directly above the red one. So this longer expression is still producing x equals 16 out of it. The next thing we could do, we could release these parentheses. We could combine like terms. This 12 and that 36 could be a 48. I think I want to get these log bases to be the same. And the way to do it, let's just kind of graph log base 16 of x and log base 2 of x. I think I want to, here, I'll just show you what I'm thinking. I'll change the 2 to a 16, and I'll put an exponent of 4 right here. And that should be the same as log base 2 of x. The one caveat is that we have this left branch here. It kind of has to do with like when you raise something to the power of an even power, you're only producing non-negative numbers, and therefore we're allowed to take the logarithm of positive numbers. So that's why there's an extra branch here appearing out of like my new expression. But besides these negative values for x, log base 2 of x and this expression right here are essentially the same. And again, my goal here was I wanted to get the same base for all my logarithms, and this just feels like the easiest way to do it for me. So I'll copy that, substitute it in there, delete all these because I don't need them anymore. Ooh, and actually I will copy this and put it here because again, getting rid of log base 2. We still have the square root sign. And my idea here is if I isolate this square root expression by like moving all of these numbers and expressions over to the left side, I can then just square both sides again, and that will remove any square roots. So let me subtract this term to the left side. I want to subtract the 48 here and make this a minus 45. Another log rule, we can take this exponent, bring it down as a coefficient, so that power of 4 can now be a times 4, and that lets me combine these as like terms. If I have 1 log base 16 of x, and I'm subtracting 4 log base 16s of x, then I can say together it is a minus 3 log base 16 of x. I will divide both sides by negative 12, and ultimately that will knock out those minus signs there. And then I just need to divide this whole expression by 12. And that was a lot of algebra steps that I just took. So just to kind of pause and look back, I do still have a green line directly over my red line from before. So that shows me that I haven't really changed the expression, at least too much. It is possible that if I keep zooming out, maybe I accidentally created a second extraneous solution by doing this algebra stuff. Especially when you're working with like logs and square roots, there's always a chance that when you square things or undo steps, you accidentally create another solution. So maybe there's another one out there that I can't see on the graph. Anyways, let's go forward with the algebra. Let's square both sides. And so I'll need to square the denominator and square the numerator. This turns into 144. Let's distribute all of this out. When we square it, we do the first times the first. 45 squared is the current year. We will do twice the product here. So that's going to be whatever 6 times 45 is. So plus 270 log base 16 of x. And then we're going to get this squared added on at the end. And I'm going to decide to call it 9 times and then log base 16 of x squared. Now, because this exponent is on the outside here, not attached to this x, I can't use the same log rule of bringing this 2 down here. It doesn't work the same. So this expression is, I believe, as simplified as possible, and it's the same thing as the stuff in the numerator. And now I have a purple line on top of the green line on top of the red line, showing me that things are still going great. Don't like fractions, so let's multiply the 144 over to the left, or the right-hand side, rather. So this number becomes 1728. We can get rid of this. Let's combine like terms again. I can subtract the 1728 to the left side. We get 297. Bear with me. I think I see the light at the end of the tunnel here. I have an idea of what's going to happen here with the algebra. And then let's see. Oh, we can use that log rule again, where the exponent on the inside can become a multiplier on the outside. This number right here turns out to be 576, and I can subtract 576 of this expression over here, and so we get whatever 270 minus 576 is. So we'll get minus 306. And now we get it equal to 0. And this, weirdly enough, is kind of a quadratic equation. I'm going to put it in standard form right now, where we now have something squared minus, or we have basically a x squared minus b x plus c equals 0. This essentially is just 9y squared minus 306y plus 297 equals 0. And I'm going to ignore the graph for this one for a sec. If I were to solve this quadratic, I would probably start out by dividing everything by 9 to get my leading coefficient to be a 1. So we can divide this by a 9 to get 34. We can divide this by 9 to get 33. This turns out to be factorable, actually. This is just y minus 33 and then y minus 1. And the whole time, y was just holding place for this right here. How about let's keep the y for one more step. This is all equal to 0. So that's all equal to 0. And then using the zero product property, this shows me that y is either 33 or 1. And substituting this expression back in, we either get log base 16 of x is equal to 33, or log base 16 of x is equal to 1. So here's actually what I was kind of talking about. We're getting an extraneous solution, I think. If we unravel our logarithmic equation here, we're getting 16 to the power of 1 is x. So x could be 16. But then this one is saying that x could possibly be 16 to the power of 33, which is an obnoxiously big number. If we imagine what would happen if we used this number here, we could plug this in back there. And that actually, this just shows me that this number maybe is a 33, right? Log base 16 of x could be 33. We could substitute a value back in here. Oh, Quill just joined me. And I think that would tell us that log base 2 of x is going to be 33 times 4. Essentially, for every 16 we're counting over on this side in our tally, we would need 4 2's to produce that 16. So overall, we're going to get 132 2's in this really, really big number. So we could test it out and see what happens back in our original equation, and see if plugging in this large value would give us a 6 at all. So like I said, this would become a 33. This would become a 132. The square root of 36 is just 6, so that's kind of cool. But then the square root, oh, well, that's a whole number too. The square root of 144 is 12. So we happened to come across an integer kind of solution here. These maybe luckily turned into square numbers and then therefore whole numbers. Maybe the idea here of like why we're coming across this extraneous solution is somewhere along the way when we were squaring our values, this 6 could have possibly been a negative 6. This could be the case if you're squaring square roots, or you're the one applying square roots to undo squares. There's always a chance that some kind of positives or negatives are going to go awry. And so that's my guess. I'm not exactly sure what step did it, but my guess is that the algebra of squaring things accidentally allowed this first expression to possibly be a negative 6, and this expression to definitely be a positive 12. The reason why this is an issue, though, is that we're never going to get a square root resultant a negative resultant out of a square root expression. You're always going to get a number that is 0 or greater, as shown by like this graph, right? Our values are only ever going to be above the x-axis. So that's why we can throw out this idea of log base 16 of x being 33. That's just way too big. This one was the one that worked out. And then once we unraveled the logarithmic equation into an exponential equation, we get x is just equal to 16 for today. So that is the algebra way of solving it. Takes a while, takes some work. So maybe it gives us or gives some validity to the guess and check method. But I at least wanted to show two different ways. Anyhow, thanks for watching. I think I'm all done, and I'll see you tomorrow.